Right, okay, so there is a little bit of electricity in this topic that we need to have a look at. So we need to talk about circuits and we need to look at how they work. So first of all, a complete loop is required for a circuit to work, and I'm sure you remember that when you were making circuits back in year 7. When an electric current flows in a circuit, the current is the movement of charge around the circuit, and the charge is carried by the electrons. The size of the current is given by the charge passing a point in a circuit each second. The higher the current, the higher the number of electrons moving past the point each second. So a way I sort of try to explain it is that if you're all in a classroom and there's about 30 of you, then you could actually represent the electrons actually flowing around, and you'd have to have a complete circuit. Okay, so just remember that for in a minute when I talk about resistance. Okay, so let's just have a look. So let's just have a look then at resistance and what we mean by that. Resistance is the measure of how hard it is to get a current through a component in a circuit at a particular voltage, and this is called the potential difference. And it is measured in ohms, and you'll see that funny little symbol there. That is the unit of ohms that you must use. So the current through a circuit can be controlled by varying the resistance in the circuit, and you can do this with two things. You could first of all have a fixed resistor, which means a component whose resistance is constant. A higher resistance will give a smaller current for a particular voltage. Okay, so if you think about it, it's a bit like, as I just said, if you were the electrons, and let's just say I asked you all to walk out the door, then that door would be offering resistance. As long as I left that door as it was, it would be a fixed resistor and it would be resisting you walking out. However, if we look at a variable resistor, or something called a rheostat, that has a resistance that can be altered. Okay, so a current that flows can be changed by simply moving the sliding contact of the variable resistor from one end to the other. So if I actually then decided to half close the door while you were walking out, and then quarter close it, and then maybe open it out again, I am offering variable resistance to you trying to get out of the classroom. So resistance can be changed by using different wires. Longer wires have higher resistance than shorter wires. Thinner wires have a higher resistance than thicker wires. So if you increase the resistance, this decreases the current. So if you think about it, if I closed the classroom door more, it means less of you would be able to get out, because you would be the current carrying the charge. And decreasing the resistance increases the current. So if I open the door, then you'd be able to get out more because there's less resistance, and so you would have more flow. Now this is the equation that you need to use. Now you'll find this at the front of your exam paper. However, they don't always, well, they won't put it into a triangle like we have there. But I do suggest that you do this, because if they asked you to work out the current of something and they gave you the voltage and the resistance, you might get a bit confused, and it's always good to put them into a triangle. Okay, so for a given resistor, current increases as the voltage increases, and for a fixed voltage, current decreases as the resistance increases. Now the next part of this topic is looking at a plug and looking at what all the wires do, and you should be able to describe these. First of all, you need to know that there are 230 volts going into the plugs in our homes. It used to be 240, and you might still see that in some textbooks, but it's actually 230 now. If you looked inside a plug, there are 3 wires. Okay, first of all, there is the brown wire that you'll see over on the right hand side, and that carries the current to the appliance at a high voltage, and that is called the live wire. If you look over on the left hand side, you'll see the neutral wire, and that is blue. Okay, and this just completes the circuit and carries the current away from the appliance, because if you remember, you have to have a complete circuit. And then lastly, the wire at the top, the green and yellow, you must put both colours, is the safety wire that stops the appliance becoming live, and this helps to take away the excess charge. The other thing you'll notice there is the fuse. Now the fuse has a very thin piece of wire running through it, and if too much energy goes into the appliance, then that fuse will break, so that your appliance doesn't become damaged. Now each fuse has a rating, and if the current passing through it exceeds this rating, the wire inside the fuse heats up, melts and breaks the circuit. Like I said, this protects your electrical appliances from surges of current. So the fuse melting, a little like 10p fuse, is much better than a £100 electrical appliance. So if you had a fuse with a rating of 13 amps, it would melt if 13 amps were to pass through it. A 3 amp fuse contains a thinner wire which melts when the current reaches just 3 amps. It's important to select the correct fuse rating for each appliance. And that's as I've just been talking about fuses. It's a safety device. Okay, and I've talked about how they work. And then, right, the last thing here then is looking at choosing the right fuse. As I've just mentioned, you must have the correct one. Now, to do this, you can work out the current for the appliance. First of all, you will notice on your appliance how many watts of power it takes, and if you know the voltage as well, then you can actually work out what the current is, the amps that would be needed for that particular item. Okay, we've mentioned this before about earthing when we looked at safety with electrostatics, but also when we looked at the earth wire in a plug. The earth wire is another important safety device. One end of the wire is connected to the metal case of the appliance, and if the live wire were to come loose and touch the case would become live, and if you were then to touch the case, you could receive a very dangerous shock. With the earth wire attached, the case cannot become live as the current passes down the earth wire, and this causes a surge in current, and this then will melt the fuse. So the fuse melting is much better than you blowing up. Now another thing about fuses, while we're just talking about that, is if in your homes you've probably, where your electric box is, that's called a circuit breaker, where it's got the little sort of flicky switches. It works exactly the same as a fuse and is connected to the live wire of a device, but rather than heat up, it detects tiny changes in the current when there is a fault, and then it will break the circuit, and that's why the little switch will flick off. Despite being more complex than fuses, circuit breakers have a number of advantages. They switch the current off much faster than fuses, and they can be easily reset and used again, which is obviously really important. Double insulation is something that comes up more often now. An earth conductor cannot become live, and this is because earthing means connecting the conductor to earth, which takes away any extra charge. All appliances with outer metal cases have to be earthed. However, the outer cases of some appliances are made of insulators, so the cables only need 2 wires because the earth wire is missing. These appliances do not need to be earthed because they are double insulated, so even if the live parts touch the case, it doesn't matter because the case is an insulator. So please remember, a double insulator has not got an earth wire.